So I'm the kind of person that would, in a past life, before I had children, would go and play a board game that would take 8 or 9 hours. There was this game that I used to play with my friends called Twilight Imperium. If you've never heard of it, I don't even know how to begin to describe it. It's like this spacefaring galactic domination game, and you have to do things like resource management and politics and like taking over planets and stuff. So there's warfare and politics and resource management, and it's over the top. We would sit and just play it for 8 or 9 hours straight, and that would be how long it would take to play the game. And now if I can pick up a game and play it for 30 minutes, I feel like I've got a lot of time put into it. All right, so first of all, hello everyone, and welcome back to Comp 2160. We're going to take a look at the term test first today. And then after that, I'm going to give some time for asking questions about assignment 3. I know I said I'd give you time on Monday to ask questions about assignment 3, but I feel like it kind of makes sense to let you ask questions now if you have questions before the weekend comes where I'm not going to answer emails and stuff. So if you have started working on assignment 3 or if you started thinking about it, I'll give you some time to ask some questions, and then I'll give more time on Monday for questions, but just in case you got some questions now. But after that, we're going to start taking a look at profiling. And if you want to follow along with me, we're going to be running some software on Aviary that will require a graphical user interface. So if you are planning to follow along on Windows, if you've installed the Windows subsystem for Linux, you're good to go. It should work. If you're on Mac OS, you need to install this software called Xquartz. And then if you're on a Linux machine already, then you're good to go. It's set up for you. If you want to follow along on your own machine, if you want to install stuff on your own machine and just do what we're doing on your own machine, you'll have to have valgrind installed, a compiler, and then this software that's called kcachegrind. If you want to do this on Mac OS, you can use Homebrew to install the package that's called gprof. It's not a typo. The software is called kcachegrind, but the Homebrew package for some reason has been labeled Q. I don't really know why, but you'll also have to install valgrind. If you want to do this on Windows Subsystem for Linux, you should still be able to use the same command to do that. Yeah. If you want to do this remotely, then you'll have to open up that Ubuntu or Bash terminal that comes with Windows Subsystem for Linux for this to work. If you just open PowerShell with your terminal, then it's not going to work the way that you want it to. If you're connecting to Aviary. So we're going to be connecting to Aviary with SSH, but we're going to pass a different flag to SSH to enable remote GUI applications to run. But you have to do it from within the Windows subsystem for Linux. So if you have terminal installed in PowerShell, you can run SSH, but what we're going to do is not going to work. But if you run the same SSH command inside of the Windows subsystem for Linux, then it will work. Yeah. Okay. All right. Okay. So what I want to do now is spend some time taking a look at the term test, just kind of stepping through it. Before I get to the term test, I wanted to show everyone this. I feel kind of proud about this. It says, "This is a bribe. Franklin, please give us a sample or even a previous final exam. Please, thank you." And I got this yesterday. And what was attached to this was the stickers of Jake and Finn. I promise that I will talk about the final exam next week. I really promise that I'll talk about the final exam. I'm even going to tell you kind of like what the major part of the final exam is going to look like, but I don't want to talk about the final exam today. I don't want to talk about it today. In terms of giving you previous final exams, the previous final exams that have been given by other instructors are their intellectual property, and I don't have permission to share those final exams with you. I can give you an overall idea of what the exam is going to look like. I can give you some ideas of what you can work on to practice in terms of programming and stuff. I can offer you to give you informal feedback. If you want to do some practice on your own and then send it to me by email, I'm very happy to give you informal feedback about that in advance of the final exam. But thank you for the stickers. Whoever dropped this off, thank you for that. And thank you for making me feel good about getting a bribe. There's always that joke of somebody stapling $10 bill to their final exam. I've never seen that happen. I think it's just a joke and a rumor, but thank you for the stickers. I appreciate that. So let's talk about the term test. What I'm going to do here is I'm going to go through the term test question by question. And what I would like to do is just kind of make sure that I am stopping and making sure that if anyone has any questions about what I am doing or what I'm describing on these questions, that we can get clarification right away on what's happening. You've already got some feedback on CrowdMark. So you have the feedback from CrowdMark in your inbox already. But I think it's worth taking a look at this together. So I'm going to start with this very first question here. This was the learning outcome that I was assessing here was apply good programming practices to produce readable and modifiable code in a programming language that makes it easy to write unreadable code. And the question was, here's a function signature, and the function is supposed to, count every time we find this character in this string, and this is the length of the string that's being passed to the function. And the question that I'm asking here is, what kind of loop do I want to use for this and why? So I'm going to rule out immediately that the recursion option was an option. I think that would be kind of funny if you did this with recursion. And if you were writing this with Lisp, you would do it with recursion. But we're not learning Lisp, and we're not doing it with recursion. So the two options here are trying to balance between, is this an event-based loop, or is this a loop that's going to have to do the same operation to every single character or every single thing in the sequence that we've got? The first option here, a for loop because strings are dumb arrays of char. A for loop is an option, yes, but because strings are dumb arrays of char, doesn't really answer the question that we're looking at here. Yes, they are dumb arrays of char, but that's not really an answer to why I would choose a for loop. I'm going to skip option B here, a while loop, because the event is reaching the null byte at the end of the string. This is an event that does happen related to strings, but this is not the specific event that we're looking for here. So this one is not an option. The event happens each time we see the character in the string. So this is a potential option. It's a potential option, but when we've got this idea of a while loop being an event-based loop, the event is the termination condition for the while loop. So in that sense, if the event happens every time we see the character in the string, the while loop that we would write for this would just terminate the first time we found a character that matched that thing. So what that leaves here is option B, a for loop, because I need to inspect every character. I have to look at every character and see if it's equal to the character that's been passed into the function. Is that okay with everyone? Any questions about that? All right. Whoops. So the next question here is it's just at the bottom of the screen. I've got a program that prints out lots of output to standard out, and I want to read it with a pager, like more or less. So remember that these are programs, more and less are programs that will let you read the contents of a file, and it does it one single page at a time. Both of these pagers, so both of the pieces of software read from standard input. So the question here is about sending data between two different programs. There's a statement here that says, I don't need to save the output from the program. Which redirection operator should I use? So redirecting just output here, this one, option C, This one is not going to be quite enough because this is redirecting output to a file. This is redirecting standard output to a file. So option C is not going to work. Option D is redirecting output from a file, redirecting a file to be standard input for a program. So that by itself is not going to work because we're talking about two different programs that we're trying to connect together. So that leaves the three options: redirect output and then redirect input and then redirect output, or using a pipe for option E. Redirecting input then output for option B here. This one isn't going to work because we're trying to read from standard output to begin with at the start. So option B isn't something that we want. Option A and option E are the last two that are left, but really specifically I'm saying I don't need to save the output from the program. So because I don't want to save the output from the program, I really don't want to work with file redirection operators at all. And so the only thing that's left here is for me to send data between the two programs with a pipe. So if the program here, for example, is called something like my program, the command that we're actually going to get here is something that looks like my program, and then pipe, and then less. So I want to send data from the standard output of my program to the standard input of less, and I don't want to save any files while I'm doing that. So just connect those two things directly to each other. Is that good? These two questions were done fairly well on the test, so I'm not too concerned about them. All right, so here is a little code sample, and then there are some questions that are related to this code sample. The first part of question 3 was asking about building and executing programs from a command line environment. So the question here was, here's a sample of code. If I were to compile this code with Clang, what might get printed out if I compiled this code with a wall flag? So wall was something that we're passing to Clang every time we run it now. I wasn't looking for you to necessarily reproduce the error or the warning or whatever that would get printed out. I wasn't looking for you to transcribe exactly what it said. I was looking for you to broadly identify the issue that we have on line 22 here, and then I'm going to scan just ahead here, and then also on line 30. So on line 30, we're returning this stack allocated array from the function in string copy. And so the warning here would be something like returning, it's a warning. And the warning is about returning a stack allocated address or object, something to that effect. The graders should have given you half marks if you wrote that there would be a warning that gets printed out, but didn't really say much about what the warning was. But the warning that I was specifically looking for here is that there's something about stack allocated addresses being returned from a function. Is that okay? Okay. The output. So what might be the output of this code? So there's one printf here that prints something. And what I was looking for here is part B and part C, which is the draw the big picture question. These are kind of related to each other. I was accepting two outputs here. The first output that I was accepting was Pikachu. So this is the first %s here. This is 1. Then Snorlax. That's the second %s here. That's 2. And then copy 1 and copy 2. The output that I was expecting is that it would just print out the same string 3 times after that. This is what I would expect to see as output when we compile this with Clang. If you compiled this with GCC, the other option that I was accepting, because that is a possibility, is that it might print out Pikachu, Snorlax, and then it might print out null and then null like this, like actual printing out the characters in parentheses, null, null. This is the behavior that we would see with GCC. We haven't been using GCC in this course, so I wouldn't expect you to do that, but I accepted it because you might have seen it before somewhere else, that kind of behavior with that. So this output here, and I'm going to move ahead to the next page. The output here is kind of related to the next question here. So why is this the output of the code? The why is this the output of the code involves us taking a look at the runtime stack and how it gets changed as the code is executing. So what I was kind of looking for you to do here is to start to draw something that looks like a runtime stack. So I'm going to start drawing something that looks like a runtime stack here. I'm going to start way down here, and the very first thing that I'm drawing here is for the main function. The main function has a couple of strings that have been allocated. There's 1 and 2. And 1 and 2 are pointing at Pikachu and something like Snorlax here. There's also 2 stack allocated pointers. So these are 2 pointers to string or 2 pointers to characters. We've also got copy 1 and copy 2. So copy 1 and copy 2, I'm going to make this a little bit bigger, I think. So 1, 2, copy 1 and copy 2. So copy 1 and copy 2 are just, they've been allocated here, but they haven't got anything assigned to them yet. It's when we start calling the function that we're going to start allocating stuff for them. So if I go back here, the code calls string copy twice. It's calling string copy once, and then it's calling string copy another time. So the very first time that it calls string copy, we're going to add a stack frame to the stack, to the runtime stack. And what we're adding to the runtime stack here is an address for this original pointer that's being passed to us. We're allocating this entire array of characters, and we're allocating this integer counter here. So I'm going to pop back to my diagram. And what a stack frame for string copy looks like here is going to be a pointer for original. And original, the very first time we call it, is going to be pointing at this Pikachu that's way off over here. It's going to allocate an integer for size. Cur. And then it's going to allocate an array that's 10 elements long. This is way more than 10. I want it to be 10. And then I'm going to put ... length 10. So I want this to have 10 elements in this array. This is what's being allocated on the stack for the stack frame when we call string copy. The string copy function is then it's going to go through and it's going to copy all of the characters from Pikachu into this stack allocated array. So I'm going to start that, but I'll stop halfway through. I'll copy them all, okay? And then what it returns to our main function, what it assigns to copy2 is going to be the address of the start of the stack allocated array. So here what I would expect to see is something like copy1 or copy1 now points at the beginning of this stack allocated string. Once we return from this, after we return from this, this stack frame is going to get popped off after return. But the observations that we've made in class is that once it does get popped off after returning, it doesn't change the values that are here. It just kind of leaves everything in the same state that it was before. So on the next copy, the next call to string copy, I'm going to say next call to string copy. What this is going to look like is we're still going to have our stack frame for main. Main is still going to have 1, 2, copy 1, and copy 2. And copy 1 and copy 2, right now, copy 1 points at the contents of this Pikachu up here. So it's got P-A-K-I-C-H-U null byte. As we call string copy, we're going to have that same kind of block allocated here. String copy, whoops. And what that's going to do when we call it is that original is pointing now at this other string that we've got here. We've got that cur variable again. And what it's going to start doing is I'm going to say that this is going to get transformed into this one. And it's going to start copying Snorlax, null byte, and copy 2 is going to point at this, but they are now equivalent to each other. So both of these are the same. This one has been overwritten by the contents of this. So I'm going to move this arrow just over here. Overall, this mess of a diagram is kind of what I was expecting or hoping for you to be able to show with this. We're doing this stack allocation. We're pushing a stack frame on. The array is contained within this stack frame. And the next time we call it, we're overriding this same stack frame here, the same array that's been allocated in the stack frame. And both of these pointers are pointing at the same contents. Any questions about that? Yeah. When a frame is put on the stack, it's never resized. It makes a location for everything in, for example, for the main function, it'll do everything for the main function. Yes. Like a placeholder for everything. Yeah. So the question is, ultimately, do stack frames get resized after they've been added to the stack? And they don't. The size of a stack frame actually gets computed at compile time. So when we've got code like this, the stack frame for main will have been pre-computed by the compiler as enough to hold 4 pointers to character. The compiler will have pre-computed this stack frame to be 10 bytes for characters plus however many bytes for an integer. This part is not actually technically part of the stack frame in that it just lives in the original thing. There might be a copy variable if you make changes to it, but ultimately is going to be the variables you're declaring at the top are going to be the size of the stack frame that gets computed by the compiler. Yeah. Which is what kind of goes back to that weirdness of if you use strlen as the size of an array, it's not actually being allocated on the stack because that's something that's getting computed at runtime as opposed to at compile time. So it's functional, but it's doing something that we're not expecting it to do. Yeah. Any other questions? All right, awesome. Okay, so I'm going to skip past the bottom of this page. And I'm going to start taking a look at the public interface that's been defined here. And the public interface that's been defined here is something about a sequence of numbers. In terms of the design by contract that we're trying to apply to this, we're kind of given this function prototype, and then we're going to be trying to think about things that are required as input for this function prototype. The tests that you have, please remember that this word here and this word here were different, but I've just changed that in this document. So in the one that you're looking at on your screen, it might be different still, but I made that announcement during the test so that everybody should have that same information. The preconditions for this are going to be that we are taking as input an array of numbers and then the size of the numbers that we're passing in. So the kinds of preconditions that I was expecting to see for this are things like length is positive or length is greater than or equal to 0. So I can't or shouldn't be passing a negative number into this make sequence function. I would expect it to be that the length is positive or greater than or equal to 0. I'm expecting that numbers does not equal null. So I have to be passing something to this for it to work with, but I don't want to get null in here. Another one that that should have been accepted or that I would have accepted here is that numbers is equal to null, and these are kind of combined together, and length is explicitly equal to 0. So we might want to make a sequence that has 0 elements in it. And if we're passing 0 elements to our sequence, then it should also be a null thing. And that would be something that we could check inside this. So these two right here, these were each separate things. This is another one, and this is another one that, that I would have accepted. Any questions about that? Okay. Oh, the other one, sorry, there's one more that I was accepting here. The other was that given that we have the structure defined here on part B, is that we know that there's this max sequence length thing. So another precondition that I accepted here was, sorry, I'm trying to go back. Another precondition that I accepted here was that that length is less than max sequence length. Okay. So once we've got our preconditions, then we're moving on to the invariant part of this. And for the structure that we've got, the things that I was looking for here were that kind of related to the preconditions. So once we have created a valid sequence object in our program, before we return it to a client, the invariant for this object is that length of the sequence must be greater than 0, or again, the length is equal to 0, And actually, that's it. The length of the sequence is greater than or equal to 0. So because the structure here is defined as an array, as opposed to a pointer type, we can't have sequence be null. So the length of the sequence here is the main property that we have for an invariant for this thing. We may have also said that a valid sequence here is one that is not equal to null. So a valid sequence object is not equal to null. The other one that we could have had here related to length is that length is less than max sequence length. And that's the invariant that I've got for this. We okay with that? Any questions? Good. Okay. And then the two post conditions for the function. One of the post conditions for this function is that the sequence we are returning is valid. So it passes the invariant. When I'm going to send something back to my client, I'm telling them that you can expect that this thing should be a valid object as I've defined what a valid object is. So one of the post conditions for this function to create one of those is that it is still a valid sequence or that it is a valid sequence. That then might be separately something like that the sequence is not null. It might be that all of the contents of the original array are in the sequence. It might be that they're all in the same order. And because we didn't specify that the numbers array was constant, one that was also valid here was that the contents of original array are not modified. This very last one here, the contents of the original array are not modified, is probably not something that I would accept on a final exam question that's like this, because I would mark it with const because we know about const now, as opposed to, you know, having that crazy set of if-def to copy the contents of the original array and then verify that it's still the same at the end. But because in the state that we were in for the term test, we didn't have that yet, that's a reasonable thing to write down for this. Is that okay? We're good? Okay. The programming part, there were a number of common errors that I saw when I was taking a look at the test. And this isn't to be like shameful or anything. I'm not trying to shame anybody, just kind of like the way that things are changing for second year courses as opposed to first year courses maybe. A lot of people spent time writing a main function for this code, and that wasn't necessary for this. When I'm saying implement an interface, I mean just the interface. You don't have to implement any supporting code for a main function. For this structure, what I was expecting you to do really generally was to define a function, either define a function for the invariant, so create a new function that takes the invariant that you described on the previous page and then actually be able to enforce that by calling it. I was expecting you to write assertions for the preconditions and post conditions for the function, minimally the ones that you had listed in your previous page, and then to do some defensive programming around the inputs that you're getting. So using conditional statements to also make sure that the data that was being passed in and then the dynamic memory allocation that you were doing was successful before you started to try modify the contents of this thing. So what I was approximately looking for here, I'm actually just going to type this out rather than write it because my writing is terrible. My writing is terrible, and I think it's going to be a little bit better if we can actually read what I'm trying to get across here. So I'm going to switch to my terminal instead of this, and I'm going to start typing in Vim here. So I'm going to make it bigger. Is that big enough at the back? Thank you. Okay. The beginning of the code kind of has the includes already, so I wasn't expecting you to rewrite those includes. You could really start by writing the function itself or the precondition, the invariant for the object. So for me, the invariant for the object looked something like this. So I would have void validate. I'm going to write this just as a C file, w test.c. So it would be something like void validate sequence, and it would take as input a sequence pointer. And then I'd go through the process of validating my sequence based on the invariant that I defined above. So that would mean things like asserting that the sequence object is not equal to null, asserting that the length of this object is greater than or equal to 0, asserting that the length of this is less than max sequence length. So this is the invariant that I've got for the actual function itself. So this is a function that returns a pointer to sequence. It takes as input original set of characters. So I'm going to write numbers here and a length. And as preconditions, what this is doing is checking the values that were being passed into this. So assert that numbers does not equal null. Assert that length is greater than or equal to 0. I'm going to say separately greater than 0, or length is equal to 0 and numbers equals null. I'm going to combine these things together. So I'm going to say numbers does not equal null and length is greater than 0, or the length is equal exactly to 0 and the numbers is equal to null. So those are the two cases that I've got as the preconditions there. I also want to assert that the length is less than max sequence length to make sure that I'm not going to overwrite everything that I've got. I'm not going to go past the end of the array that I'm allocating. Then I'm going to go through the process of declaring a variable for the sequence that I'm creating. And I'm going to say at the beginning that this is equal to null, and I'm going to return this sequence at the end. For the post conditions here, the main post condition is really that I want to do is really that I'm validating the sequence that's being passed back. So this is one of the post conditions that I've got, is to make sure that the sequence that I'm passing back to it is the same as what I passed in the first place. Then I'm going to go through the process of using conditional statements to verify some of what I've got. So I want to make sure that numbers does not equal null and length is greater than 0. Or length is equal to 0 and numbers is equal to null. And then once I'm inside here, I'm going to say S is equal to malloc size of sequence. I'm going to check to see that S has actually got a value here. So malloc didn't return null to us because we're out of memory. I'm going to set the length of S to be equal to the length that was passed in. And then I'm going to copy the contents of numbers to S. So I'm going to check here again if numbers is not equal to null. I'm going to say for int I is equal to 0, I is less than length, I plus plus. And I'll say S numbers at I is equal to numbers at I. I think that this is called something else. It's called sequence inside that object. So I'm just going through and copying those things. This is the overall structure of what I was looking for this. The main things that we were looking for when we're assessing this is, consistency with braces, putting comments where appropriate. There weren't a lot of places where you needed to put comments on this. You didn't need to comment the function itself. Making sure you're using conditional statements to check the results of things before you start to try to dereference them. So if you do try to do malloc, for example, and it returns null, then check before you start trying to assign properties to it using that arrow operator. Are there any questions about this? Okay. All right. If you do have questions, please feel free to email me. I don't want to put people on the spot in the classroom. So if you have questions about the way that you are assessed, or if you just have general questions about the test, please feel free to send me an email and get in touch. All right. If there's no questions about the term test, then what I would like to do is just leave a minute or two to see if anyone who started thinking about the assignment or started working on it has any questions about it. Yeah.
Make a block or so you have 16 bytes and then make blocks to fill that up. The user would take the end block, assuming they all 16 bytes, and then they were to call string copy, but fill it with something that's like 1,000 bytes charge.
Yeah.
Need to
So that's a great question. The question is, do I have it in here still? I think so. The question is, I've got this zone that has 16 bytes in it, and I'm going to say that at this point down here that copy2 pretty much allocates the whole thing. If someone does this, strn copy2, and then I'm just going to say 1,000 characters and then 1,000. So way past the bounds of, this goes way past the end of the zone. Should we do anything about it? And then the second question is, can we do anything about it? I'll answer the second question first. No, you can't do anything about it. strn copy is just writing to memory here. It's writing to the address that the person writing the code told it to, and C doesn't have array index out of bounds exception. So it's just gonna do it. It's just gonna do it. There's nothing you can do about that. And that's a limitation of C more than anything else. If we were writing this in Java, you'd get an array index out of bounds exception, but with C, there's nothing we can do about it. So to answer your first question, then also no, there's nothing for you to do about it because there's nothing you can do about it. Yeah.
Does the size of function take into account the size of all the components and materials inside of it? If I take size of, so will it automatically see the size of the
No. So if I'm going to ask this, I'm going to open the interface because I want to make sure I'm talking about the same thing as you. So there's this function that's called zone size. Here, this one. This function should just return the number that was passed into make zone in the first place. That's really all it should do. If you use size of on your zone, if you use size of on the zone type, it will tell you how many bytes are in that type. But it's not going to follow pointers and then compute how big those pointers are pointing at, because as far as size of is concerned, it knows just about the thing that you passed it. It's not recursive. If you pass size of an instance of that structure, I'm going to make sure that I'm prefacing this with, I don't know what will happen, but my expectation of what would happen is that it would just tell you the size of the zone structure as opposed to how many bytes that object actually occupies. It might even tell you just that it occupies the space of a single pointer. So whatever, I think it's like 8 bytes or something like that. If you're talking about this function, it should just return the number that was passed in originally, rounded up to the next multiple of 8. Yeah. Did you have a question?
So a zone has a data character array. So then the zone size is just with the parameter we put inside the main zone. So basically, when we are creating that character array, so inside the malloc we just input that zone size.
You need to round it up to the next multiple of 8.
So after doing that, we just put it inside the method, right? So we don't have to put it inside the malloc, and it has to assign the memory to that character array.
Once you have the memory that's allocated, you don't need to do anything to it until zalloc starts to get called. When zalloc is called, then you're going to start to zero out the contents of the buffer that was allocated to you up to the size that's being requested for allocation.
We just have to create a structure, the linked list, and the character array, and the size of that zone. That's it.
Minimally, yes. You may want to have more than that. My structure has more than that, but it's minimally enough for you to have those 3 things, yes.
So we have to do all the stuff inside the zone.
Yeah. Okay, good.
So block size is the size that is related to that each node of the linked list.
Yeah, so every node represents a block or an allocation. I'm trying not to use these words interchangeably, but
zone size is just the size of that character array. Is it so?
sorry, can you repeat the question?
Zone size is just the size of that character array.
Yes, the size of this zone size is the number of bytes that's allocated to the entire zone. So that's the buffer that's in the zone. Block size is how many bytes does this specific allocation have?
It's more than the size we are left in the character array, then we just simply return from that function, because we can't allocate that.
Yeah, that would happen here in the zalloc function though. So you're going to be trying to find free space using that first fit allocation policy in this function. And if you can't find free space, so it exceeds the amount of space that's available, or there's just not enough free space in between everything, then at that point you would return null from this to say there's I couldn't do that allocation request. Okay, good. Yeah.
Are the block size and zone size functions really supposed to be static?
It's a good question. Are the block size and zone size functions supposed to be static? All of these functions that are in the .h file can't be static because we're going to be expecting to call implementations of those functions. You will at least have an invariant for your zone object. That should be static. I shouldn't be able to call that from my code. You probably want to have an invariant for your node type. I shouldn't be able to call that. I shouldn't even know that you're using nodes internally. You may want to have functions that will do things like first fit, as opposed to trying to jam all of this into zalloc. So do first fit in a separate function from zalloc that you're calling. I shouldn't be able to call that function. If I know that it exists, I shouldn't be able to call it. but all the functions that are declared in this .h file must be not static. Yeah. Any other questions? Yeah.
Should we worry about the upper bound of the unsigned short data type when making our zones?
So the question is, should we worry about the upper bound of zone size t, z size t? I mean, if you check to see if it's greater than this, it's always going to be false because the compiler is just going to like either fail to compile it in the first place because the size that you're passing of a number is too big. Like if I pass, I think the max size for short, again, don't quote me on this. I think it's like 16,000. It might be 32,000 because we're using unsigned. If you pass 64,000 to this, I don't think your code's going to compile. If you try to compare this to 0, if you say that it's less than 0, it's always going to be false because it's an unsigned type. So it's never going to be less than 0. So we're encoding some of this stuff in the type itself as opposed to having to use assertions to check things. You can't compile it with these weird values. I think you probably could pass a negative value to this, but then your compiler is just going to turn it into a positive value. Yeah. Any other questions? Yeah. So the question is, do you want us to make another linked list.c or linked list.h? If you want to, when I wrote this, I put it all into zones.c. If you want to have a separate linked list structure from your zone stuff, that would be okay. But I think that you're going to be looking at adding more complexity than is necessary. If you did that, then I would expect you to do like an appropriate interface for your linked list, and that you're not just calling functions, you're not just using properties of the linked list inside your zone at that point. When I wrote this up, I just put the structure for the node inside of zones.c so that I could just manipulate the list inside of my functions as opposed to having to write all this extra support for like insert after or delete or whatever. I could just do it inside that file. Yeah. Any other questions? Okay, all right. As I said, I will give you more time for questions on Monday. I'm kind of guessing the weekend is going to be the big work time that you got for this. So I wanted to make sure that you have some time to ask questions now before, but then I'll make sure you have some time to ask questions later as well. All right. Okay, so as I said before, if you want to follow along with the profiling stuff that we're doing, you're going to maybe need to do some setup. If you're using Mac OS, please install this export software. If you're using Windows, please make sure you're using an actual Windows subsystem for Linux terminal. If you want to do this on your own machine, you're welcome to do that, but you'll need to install some software before we get to it. Excuse me. So by the end of today's lecture, what I am hoping for you to be able to do, this is both continuing and beginning. I want you to be able to given an existing solution, I want you to be able to identify and explain where the use of appropriate data structures, algorithms, and/or techniques such as caching and lookup tables provide better paths to optimization than low-level code. The goal for today is really just identify where the problem is. Identify where the problem is. That's what we're looking at today. I've got some examples that I will show you. Maybe this class, but maybe next week, that are kind of like places where we could very quickly change the internal data structure of something and then get a very quick speed up for this thing. But for today, we're mainly just going to be looking at the use of profiling tools. So put yourself into your mind theater of you're in a state where you have written some code and you actually know how it works this time. So when we were doing debugging, we wrote some code and maybe we forgot because of past self, we've got that bad relationship with our past self and we didn't do a good job of commenting at the time. But this time we know how it works. And it works, but it does it really, really slowly. So some part of the code that we've written is not able to get done what it needs to get done in a reasonable amount of time. Maybe you're in a state where you have written some code and you don't see that it's working slowly, but you give it to your friend, and your friend has either found a way to make your code crawl, or alternatively, your friend has a really janky laptop that they have, literally got tape on this corner of their screen. It's 10 years old. It's got a really shitty processor in it. And the code works great on your laptop, but it works terribly on theirs. And it's not just because it's a 10-year-old processor. Or maybe you've been given some code that someone else wrote, and maybe that person understands how it works, but when you try to use it, it's agonizingly slow. So someone's written a library for you, they've given it to you, and it's your job to start working with it. The things that you can do when you're in this kind of a situation are to spend some time doing some cave diving, spelunking into your code, using printf, or question mark, question mark, question mark. Spelunking again here, when I'm thinking about spelunking and cave diving, is really just spending time rereading your code. Yes, you understand how it works this time. Yes, your friend can explain to you how the code that they wrote works. But we're still taking the time to step through it. I know how this works, but it's obviously not doing something that I'm expecting it to do. And the thing that I'm not expecting it to do this time is going real slow. So take the time to read the code and manually and mentally execute this using pencil and paper, and start to think about, where am I doing a lot of extra work that I really need to be doing? So where am I doing a bunch of extra work that it could, at least in my mind, be something that is much faster or much fewer operations overall? The other option is to use printf. Add a bunch of printf statements to your code, and what we're looking for this time in terms of application flow is not like, how do we get from A to B, but how do we get from A to B, and where does it stop printing before we get to C? Or where does it start really, really slowing down as the print statements are coming out before we get to this point C in our application? Similar to debugging, we are trying to understand how our application is moving from one place to another, but as opposed to observing variables in the state of the application in this flow, we're really just trying to see, where does things slow down as it's going? One of the problems that we might have with this is that it might not be observably slow. We might have a program that runs for a long time. The software that we've written in this course so far has been like, you hit the enter key and it's finished immediately. Software doesn't always do that. We've got apps on our phones that just sit there running kind of all the time, and they don't necessarily look like they are running slow in any specific spot, but they might be running slow in the long term. So what happens if we find this case where this isn't observably slow? We can't see that printf is slowing down anywhere. So what then? Just hit BMO. Poor BMO. Poor BMO. Hit BMO with a paper. Where we had debuggers for debugging software to help us better understand the state of the application and the flow of the application, profilers are tools that will help us how to identify parts of code that is slow. It's going to help us identify parts of code that are slow kind of in a granular way all the way down to functions. There are many different profilers that are out there. This is a Wikipedia page that is a list of performance analysis tools. And you can see that there are many, 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 many different profilers that are available for use for different programming languages, for different environments. So if we go up to the top here, we've got profilers that are working in places like iOS and Android, or Linux and Windows. We've got things that are specifically targeting different kinds of programming languages and environments. There are many, many different kinds of profilers. In this course, we're going to be looking at two different profilers. The first one is called gprof, and I don't really like gprof very much, but I'm going to show it to you because it's there. And the other one is valgrind, and valgrind is the one that I would prefer to use just in general because it's easier to use than gprof is. Let's take a look at these two different applications. So the first one is gprof. To get gprof to profile your code, you got to do three things. And this is one of the places that I'm going to invite you to follow along with me. The first is that you add a new flag to your code and the new to your compilation command. And the new flag that you add to this is -pg. So -g says includes debugging symbols, and -pg is profile. So profile this code with gprof. Once you have compiled your code with this PG flag, you just run your code like normal. You don't change the way that you're running your code, you just run it. But the difference is that when the program that got created by Clang here runs, there's a whole bunch of extra code that's been added to this file that will create this file that's called gmon.out. The code that gets added to your program by Clang is instrumentation code. So it's checking to see which functions you are calling, how long each of those function calls takes, and then it produces a report here called gmon.out. Gmon.out is not a human readable file, so then we use a program called gprof to present that to us, to read that file and present it to us. So I'm going to switch over to my terminal here. I am connected to Aviary right now. I'm on OWL, and I've got my sample solution for assignment 2 up here already. I've got a make file here. So my make file is what I'm going to modify. I'm not going to make changes to the way that I'm compiling things. I'm going to just change the make file that I've got. So I'm going to open this make file. This make file looks just a little bit different than what we have seen before in that all of the recipes do not have that list of instructions on how to compile these different things. Make itself knows how to do this. It's able to compile C programs and it's able to compile .o files. It just knows the specific rules that it needs to do that. So I don't have to actually add anything there. What I'm going to add here is I'm going to add -pg to the end of this. So I'm going to add -pg. When I run make now, cc, this is a variable that refers to the C compiler that we're using. We're using Clang. C flags are the flags that are going to be passed to the C compiler that's being run here. So I've added -pg to my C flags. I'm going to quit my make file, and I'm going to make this code. Make has gone through. It's figured out the dependency hierarchy or the dependency chain for all of these different things. And it has added this -pg flag to the compilation command that it's running. So I've got in my folder now the programs that have been compiled. The programs that have been compiled now have this extra code in them to instrument which functions are being called and how much time is being spent in each of those functions. I'm going to run the colors program, and I'm going to pass to it data files, and I'm going to pass to it happy.txt. It runs, it prints its output, and it finishes. And if I list the contents of my directory right now, there's this extra file here that's called gmon.out. So my program produced this when it ran. I want to run gprof on this. And to run gprof on this, I'm going to say gprof and then colors, the name of the program that I had previously run. gprof just kind of dumbly prints everything to standard output. I'd like to be able to read this, so I'm going to pipe my output into a pager like less. And what you can see here is a summary of what happened as my code was running. What this shows me is that they all took about 0 seconds to run, which is fine because they're not doing very much right now. When we press the enter key on our keyboard, the program ended immediately. There's not a lot of work that's going on in those. But what we can see is that validate stack got called 85 times during the execution of this program. The push and pop functions got called each 25 times. And that, when we think about what we were doing here with bracket matching that matches perfectly, this was that happy path case, it makes sense that we would call push 25 times and pop 25 times. At the end of that execution of that algorithm, I would expect that my stack would be empty for each of those. I created 5 stacks and I destroyed 5 stacks. I printed out a match for 5 different test cases with this code. gprof here is telling us things like, this is the function that gets called the most often in the code that you are working with. It will also tell us things like how long they took and the percent of time that things take when they do actually take a long time, but in this case, everything was pretty fast. This also tells us, I believe that what this is telling us is like the hierarchy of calls, so which calls are calling other functions. So that's gprof. I don't really care for gprof very much because it's I don't know, it is what it is. It does what it says on the box, but it doesn't do much more than that. So I'm going to disconnect from Aviary. And I'm going to reconnect to Aviary. And I want to show you what I'm doing when I'm reconnecting to Aviary. When I'm going to connect to Aviary this time, I'm going to pass a flag to SSH. The flag that I'm passing to SSH is -X. Uppercase X is a flag that says, I would like to do X forwarding. X is what used to be something called the display manager for Linux distributions and BSDs and Unixes. This is slowly being replaced with something that's called Wayland, but that's kind of outside the scope of this course. -X says, I want to be able to run GUI programs on the remote computer, but see the window on my laptop. So I'm going to do SSH-X. I'm going to pass my username, aviary.cs.umanitoba.ca. Again, you have to be running this in Windows Subsystem for Linux, an actual Windows Subsystem for Linux terminal. If you're doing this on Windows, you have to have exports installed if you want to do this on a Mac. What I can do now is I can run programs like this really fun program called Xeyes that pops up these eyeballs on my display. And these eyeballs kind of get followed around. It follows my cursor around. And so Xeyes is a program that's running on Aviary, but the display is showing up on my window. Xeyes is a process that's running on Finch, but the display shows up on my machine. That means I can do things like, I can't run Firefox right now because I'm running Firefox on my own machine, but I can do things like, I'm going to change into this comp2160 assignment 2 solution. I'm going to edit my make file, and I'm going to delete PG, or I'm going to comment it out. And I'm going to add the -G flag here. I'm expecting this to break, but I want to show it breaking to you so that when you try to do this on your own stuff later, you'll kind of get a sense of what's happening. I'm going to write this, and I'm going to quit. I'm going to make clean. I want to remove those binaries that were produced with that PG flag. I want to remove gmon.out. Yes. And I'm going to make again. So I've recompiled everything with just the G flag this time, not the -PG flag. I'm going to switch back quickly to my slides for 1 second. We're going to do performance analysis with valgrind. And the way that we do that is that we compile our code normally or with the -G flag. So this is not PG, it's just G for debugging symbols. We run our code with valgrind, and we specify a tool to valgrind. So valgrind is a piece of software that has a whole bunch of different tools within it. The one that it runs by default is called memcheck, and that's the one that's doing that whole, have you freed everything that you allocated? So making sure that there's no leaks possible. Valgrind is a tool that will do performance analysis. It will track every function call that's being made, and it will produce a really nice file that we're going to be able to work with. And then eventually we're going to use this program called gprof to open up that file for visualization. So I have recompiled all my stuff, and I'm going to just press up on my keyboard to get back the commands that I ran previously. And what I'm going to say is valgrind -- tool equals valgrind, and then the name of the program that I want it to run. So colors, and then data files happy.txt. This is going to not work. When I run this, it's printing out this error messages related to dwarf, and then very politely it's saying, I can't recover, giving up, sorry. It's okay, valgrind, you did your best. The problem with valgrind and Clang on Aviary is that valgrind cannot read the debugging symbols that Clang is emitting by default. So I'm going to open up my makefile one more time, and I'm going to change my -g to be dwarf4. So it's not just G anymore. Now it says dwarf4. Very quickly, the joke here is that on Linux, when you compile a program, when you make a binary file for code that gets produced by Clang or GCC, the file type for that is called elf, and the debugging symbols are dwarf. Yeah. So dwarf4 is version 4 of the dwarf format. By default, Clang is emitting version 5 of the dwarf format, and valgrind just doesn't know what to do with that. So I'm going to make clean one more time, and I'm going to make it sorry, I meant dwarf-4. Thank you for that, Clang. And then I'm going to run valgrind again. It doesn't really print out very much when I run it. It gives me some extra output here. It gives me some extra output here. It produces the output that I was expecting it to. But to be able to see what it produced, we have this extra file called valgrind.out. The one that I'm going to inspect is that one. And so I'm going to run gprof, and I'm going to pass that file name to it. And gprof gives me this nice tip of the day, but then it also gives me this really great visual representation of the call stack. I don't know if I can make this any bigger, I'm sorry, but if you try this on your own machine, you'll be able to see it. Yeah, I don't think I can make this any bigger, I'm sorry. But what this shows is that what's highlighted right now is this is the main function. And these are all the functions that are being called by the main function. We also get this nice call graph that will show, like, this is the main function here in the middle. And these are the functions that main calls, and how many times it calls it, and how much time was spent in each of those functions. We can see things here like the print match function takes quite a long time to do here. So print match is down here. It calls printf, push, and pop. It called them each push and pop 25 times, and it called printf 50 times. And it spends a lot more time in printf than it does in either push or pop. I like valgrind a lot better for performance analysis than gprof, because we got cool tools like this one to be able to help interpret the outputs that we're getting from this thing. This is where we're going to stop today. So I'm going to skip over here to outcomes. You should be able to, at this point, use a profiler to generate data about your program. We're beginning to be able to do this. I want to be able to see which functions are being called the most and which ones we're spending the most time in. What we're going to take a look at next week on Monday is we're going to start to do the identify and explain where the appropriate use of data structures, algorithms, and techniques provide better paths to optimization. I hope that you all have a great weekend, and I will see you on Monday. Bye, everybody.